So, hello everyone. Welcome to another server demo. In this demo, we'll talk about Stripe Mutex or how we manage to reduce contention and love the LRU. Sorry, that was a mouthful, but I really wanted to use the title. Essentially, this is about how we reduce the lock contention on our LRU cache. Fair warning, I am going to dive into fairly low-level details from the CPU perspective. If you already know what a Stripe Mutex is and how it works, this will just be a refresher. But if you just heard the term and have been curious as to what it is or how it works, hopefully this demo will be able to shed some light into it. Okay, so we all know that we use an LRU cache for storing objects. They can be users, statuses, sessions, and various other things. Now, this is a sample code where we have 3 reader go routines and 1 writer, emulating a read-heavy workload, which reads and sets random keys for like a million times, all of it happening concurrently. That is the keyword here, concurrent. Now, let's take a look at the trace profile of the program. Trace profiles are helpful to understand what a program is doing when it's not doing anything, because CPU profiles will show what the code is running on the CPU, but how do you analyze log contention across multiple Go routines? Trace profiles are an invaluable tool for that. Okay, so here we have our 3 readers and 1 writer. We can see something strange. When the writer is not writing, the 3 readers cannot run concurrently with each other. It's almost like they're waiting for each other to finish, because like we can see like when 10 runs, 11 cannot run. When 11 runs, 10 cannot run. Well, there are sometimes they overlap, and why does that happen is left as an exercise to the reader. If you dig deep enough, you might find something interesting, like I did. Anyway, so coming back to the problem, here is the proportion of the time the Go routine is actually spent in blocking. You can see that the Go routine is actually blocked more than it actually does the work. Usually you would think that reads can happen concurrently with each other, right? Because they are not modifying anything. Well, not quite. The problem is here. The get operation takes an exclusive lock on the object. Why? Because that's an LRU cache. So it has to update its evict list every time it fetches something from the cache. Yeah, that's the problem. And this is not scalable at all. So all reads are blocked until a single read or write completes. But a single cache will have different keys, right? And we don't really need to block 2 different readers trying to read 2 different keys. So here's an idea. What if we split the caches? What we do here is that for every key, we compute a hash and then map that to 2 separate caches, each having its separate lock. So as you can see, within the 3 requests, only 2 are now blocked, but the other one goes forward without any contention. But now notice that each cache has become smaller because we have divided one big cache into 2 small caches, so objects will be evicted at a faster rate than before. As a result, we need to slightly increase the size of each cache by a certain percent. So that's one trade-off we are making here. And with that, now we see 3 readers run completely parallel to each other without any locking. And if we take a look at the proportion, that's like 3 orders of magnitude improvement. Previous one was in milliseconds, this is in microseconds. So we have come up with an idea, tested it, measured it, saw good performance improvements. Is that it? Shall we ship it? Not unless we verify a few other things. So whenever we have 2 locks side by side in an array, we experience what we call as false ship. So here's how it happens. CPU1 tries to get LRU0. And remember that when CPU fetches something into its L1 cache, it fetches an entire cache line, not just a single byte. And that's where the problem happens. So CPU1 gets LRU0 and CPU2 gets LRU1. And now CPU2 starts to write to LRU1. But CPU1 goes, wait, you can't do that. I already have LRU1 in my cache. So in spite of the fact that CPU1 and CPU2 are actually writing to 2 different areas of memory, there is actually no sharing happening. But due to the fact that they are close by in memory, they actually become shared from a CPU perspective. So the way to fix this is by adding padding to the structs, so that when the CPU fetches them, the other struct is pushed out of the cache. And now two CPUs can interact perfectly with the individual LRUs without any cache misses. But luckily, in our case, we had pointers to the structs, not just values. And as a result of that, the objects would be in random places from memory and would not interfere with each other. So we didn't need to use any padding here. And if you're thinking, does all of this really matter? Is there actually a difference? So I would invite you to run this code here and see for yourselves. Great. So now we have sharded our lock, took care of false sharing, and things are really looking good now. Can we go faster still? Of course. So let's go back to our original example. In that case, we had two structs sharing a single cache line. Now, what if a single struct is larger than the cache line? So here we have the first LRU struct having these fields: name, size, evict list, length, lock. And now the CPU accesses the struct. But hold on, we only got the first three items. The rest didn't fit in the cache line. So if the CPU needs to access the lock, which it almost always does, it needs to make another round trip to RAM. So here's an idea. What if we rearrange the fields to make the lock as the first member and push everything else as like the downwards? To be more specific, and now whenever the CPU accesses the struct, it immediately gets the lock. No cache miss, everything happens smoothly. And so with this, we arrive at the current state of our LRU cache. We have striped our LRU, took care of false sharing, and rearranged struct fields for maximum performance. And best part of it is all of it was done by a contributor, not by me. If you're interested, please feel free to take a look at the PR and its accompanying issue. There is a long conversation going back and forth for several weeks, where we went through each item painstakingly, measured the performance at each step, and finally converged on the right solution. And that's it.